Live protocol engaged.
This is my first creation, a machine built entirely from the ground up. The first time my hands have ever shaped a robot. Beyond 3D printers, beyond CNC machines, I come from a world of heavy engineering, of refuse collection vehicles, and long ago, colossal mining excavators. And when you look at this machine, you can still feel those giants echoing through its frame. But this time, I wanted something different, something personal. I forged a creature of steel and intention, technologically dangerous, like a predator, shaped by logic instead of instinct, where mechanical precision meets something almost organic, not alive, not dead, suspended somewhere in between. I call it Snack-Made 9000, born to sustain life, designed for a single primal mission, to feed a predator safely and without fear.
Alright, welcome to my new project. My name is Leon, and as you already see in the intro, I built a robot. Not because I had to, but because I love trying new things. And I want to understand how tech works behind the magic. The idea actually started when I installed a stair lift for my dad. This stair lift runs on an aluminium rail, a profile with gear teeth, where the drive wheels lock in and pull it up the stairs. And after the installation, one complete rail segment was left over. And I thought, why not build a robot on that same rail system? That's where the whole madness began. And I want to show you, step by step, how the whole thing came together, where I had no idea what I was doing, where I had to improvise, and of course, where things actually work the way I hoped. The robot lives in my kitchen, and his main task is actually pretty simple. He's supposed to fill my dog's football. Yeah, if it works, it would be great. If you could also give her a little sausage, then she's being a good girl. That's basically the main idea. But because I always want a little too much, I gave him a few side missions as well. Maybe he'll help me with guitar playing. Maybe he'll empty my 3D printer. Maybe he'll end up doing things I haven't even thought of yet. Just so you know, this is my first time doing anything with robotics. So if you see mistakes or have ideas, feel free to leave a comment. So let's dive in. Let me show you how this started and how a wild idea slowly turned into a real machine. Also, thanks to JLC CNC for sponsoring this video. More about that later. Yes, we're getting started.
Alright, let's start with the construction. I designed the entire robot in Creo, an established CAD tool, widely used in the automotive industry. The first part of the robot is the aluminium carrier profile that acts as our linear rail. On this rail, we mount the mainframe, the unit that carries the entire robot. The mainframe runs on V-groove rollers along the rail, allowing it to move left and right and serving as the foundation for all other axes. On top of the mainframe sits a rotary base, which allows the robot to rotate, and also provides the central channel to route the cables cleanly through the middle of the system. Mounted on the rotary base is the shoulder joint, a double bearing rotary module that supports the shoulder arm. The shoulder arm moves up and down, and it connects the elbow arm, which performs the same motion. At the end of the chain sits a dual scope, driven by a small servo and a simple gear setup that opens and closes both scope segments at the same time. The robot has 5 axes in total, 4 stepper motors and 1 servo. Alright, theory is nice, but let's finally start building this thing. The first step is the V-groove rollers. They are 3D printed from polycarbonate and paired with machined steel shafts that will hold the bearings later on. The rollers have small blobs on the set seam. I quickly remove them on my small lathe. Otherwise the robot won't run smoothly on the rail. I press the ball bearings into the rollers using a threaded rod, which helps them sit straight and centered. The steel shafts are made from tool steel, which honestly is not exactly ideal for my tiny hobby lathe. This machine is great for aluminium or plastic, but tool steel is really pushing it. And the tolerance actually matter here, because the rollers need to glide smoothly along the rail later. So I wasn't sure how well this would go. But I was genuinely surprised by how well this little lathe handles this material. To make the shaft usable later, I milled 2 small flats onto it, so I can actually grab it with the wrench when everything gets assembled. On both ends, I cut an external thread. Yes, I could have done that on the lathe, but that's easier said than done. Fun fact, this straight cutting set was a gift for my 16th birthday. 2 decades later and I'm still using it all the time. Anyway, the shafts fit the bearings perfectly, no play at all, and they are ready to use.
Before we jump ahead, this part of the video is supported by JLC CNC. If you ever need CNC millet or 3D printed parts, these are the people to check out. As you can see here, I've reached a point at the build where I need precisely manufactured CNC parts. All the components you see here need to be milled out of aluminium. Most of them are simple enough, but 2 parts are especially tricky: the main frame and the shoulder arm. That's where JLC CNC comes in. They have the capability to machine these parts, anodize them and ship them faster than I could ever produce them on my small machine. And the cool thing is, you can send them regular 3D files, but also full technical drawings, surface finishes, tolerances, fits, whatever level of detail you need. They can handle it. Whether it's high precision engineering or just simple milling work, they've got you covered. After I placed my order, the parts arrived just 3 days later. Over a single weekend, shipped half across the world, and they look seriously good. Like, look at this. These parts are genuinely beautiful. So, if you ever don't have the time or don't have the machines you need, consider having your parts made by JLC CNC. And if you want to try their service for your own projects, you find the link down in the description. Once again, a big thank you to JLC CNC for supporting this video and helping me bringing this machine to life. Alright, back to the build. All the other parts you saw in the animation, I'm machining those myself. I'm machining most of this part out of 5083 aluminium. It's a really nice alloy to work with, strong, stable and usually very friendly on the CNC. But I don't have enough of it. So I also have to use this big aluminium plate and I have no idea what alloy it is. Could be perfect, could be a disaster. A bit of a gamble. Before machining, I set up the toolpath in Fusion 360. That's the CAM software I use. I can build every toolpath visually instead of written G-code by hand. So in theory, everything should go smoothly. For cutting aluminium, I usually stick to DLC-coded end mills. They've given me good results in the past. Yeah, that sand mill goes straight into my collection of doom cutters. And yes, aluminium and I have some weird problems between us. Sometimes I get impatient and push the feeds too far. Sometimes I clamp the part badly and the vibrations go crazy. And sometimes, like here, I simply messed up the Z height and the tool dives 10 mm too deep. Perfect recipe for destruction. Anyway, I've got a job to do. bad, right? They're definitely not as clean as the sponsor-made parts, but for my own machining, I'm pretty happy. To finish them properly, I'm going to sandblast everything and then anodize it. It will be my first time anodizing aluminium, so I'm honestly excited to see how this turns out.
I give all the parts a rough sanding, just enough to take away the worst marks from the CNC work. To make the finish more uniform, I sandblast every part afterward. The sandblaster I'm using is honestly way too small, so it takes forever. But in the end, I did manage to get a decent surface out of it. Now anodizing. This is not a tutorial, I'm doing this for the first time, and the chemistry involved is no joke. Acids, heat, electricity, it's a kind of process where you double check everything before you switch the power on. The workflow is simple on paper, a cleaning bars to stripe off fingerprints and oils. Then into the anodizing tank, where the real magic happens. Here the current density has to be right, too low nothing happens, too high and the layer burns. The moment the power supply drops to 0 volts, the anodizing layer is done. Next comes the dye bed, 50 minutes in hot dye, gently moving the part so the color settles evenly. After that, the sealing bed, where the pore is closed and the surface locks in for good. From this point on, the color isn't coming off, at least not easily. For a first attempt, I'm honestly happy with the results. Under this brutal studio light, they look flatter than in real life. Later in the robot shots, you see the black has much more depth than it seems here.
With the anodizing out of the way, it's time to focus on the main bearing. The part where I really tried to save every penny I could.
This is the main bearing, the one the entire robot rotates on. Normally a proper turntable bearing of this size would cost €100 or more. I didn't feel like spending that, so I tried something else. I started with a cheap metal lazy Susan bearing, the kind people use for TV stands or fruit bowls. It turns, it works, but it has way too much play for a robot. So I built a second bearing around it, 2 custom halves, one of them holding the lazy Susan, boost machined and 3D printed where it made sense. Each half has a circular groove. I filled those grooves with loose ball bearings, arranged horizontally. When the 2 halves ball together, the balls carry the load on a wider diameter than the original bearing, and suddenly the wood things become incredible stiff. 0 play, 0 wobble. In the end, it's just a cheap bearing, embedded in a slightly over-engineered support system that makes it work.
Alright, so how does the electronics actually work? This robot may look completely custom on the outside, but on the inside it's surprisingly close to a 3D printer. The mainboard is a Robin Nano from my old printer. It runs my own customized version of Marlin, a motion firmware normally used in 3D printers. I removed everything I didn't need, added the features I did need, and ended up with a firmware that basically tailored to this robot. Each axis has its own end-stop switch that allows the robot to home itself and know where 0 is. Without homing, any kind of repeatable motion would be impossible. For the motors, I'm using closed-loop stepper drivers from MKS. They correct themselves in real time, so as the arm hits resistance or loose steps, the driver notices and fixes it on the fly. That stability is absolutely essential, even for a robot this small. As for power, I'm using a 24-volt supply I brought back from the dead. Some genius had drilled a hole straight through the PCB. No idea why.
To be clear, that's the idiot.
But after repairing the damaged traces, the thing works perfectly again. To actually control the robot, I wrote my own Python tools. One script lets me drive the arm with a PS4 controller, and another module can record complete motion sequences. So the robot can perform tasks automatically. I'll go deeper into that system later. For now, this is the backbone of the whole electronics that makes the whole robot move.
To move the robot we also need these cables, but I wasn't happy with how they look. So I found several sleeving options on AliExpress, and I chose the green one. What do you think? Does it work? All components are finished and ready. Mechanical parts, electronics, and even the cables are laid out and waiting. This is the final assembly phase, where everything comes together as a complete system. Let's start assembling. After months of designing, machining, adjusting and refining, this is the moment where everything finally comes together. Most days it's not really fun. After a long workday, it would be easier to just take a break, instead of spending even more hours at the workbench or behind the computer. Projects like this are demanding, mentally and physically. But moments like this, when all the parts finally come together as a complete system, make every hour worth it.
If you enjoy the video up to this point, I really appreciate a like or a comment. And if you like to see more projects like this, feel free to subscribe. It helps me know that videos like this are worth the time. The robot is now fully assembled, and after a few days of programming, the axis finally moves the way they're supposed to. I can rotate the robot, move it left and right along the rail, control both arms independently, and open and close the shovel. I can also store individual positions, and when I have several of them in sequence, the robot can reply simple motion routines automatically. My custom control software still crashes occasionally. But overall, the system is already surprisingly reliable. But is that enough to fill Yuki's bowl?
As a first task for the robot, I wanted it to distribute sausages. For that, I built a small sausage dispenser that automatically feeds the next sausage after one is taken, at least in theory. Everything you see here is still remote controlled. I'm not ready to fully automate tasks like this yet. Whipping the sausages turned out to be a real challenge, but with a lot of practice, it's gradually started to work better. Once the snack was securely held in the scoop, distribution becomes surprisingly reliable. The dogs were far more curious than I accepted. They weren't afraid at all, which was actually my biggest concern at first. But a robot that hands out sausages is apparently just too tempting. One of the whippets went absolutely crazy for the robot. He kept trying to steal the sausages whenever he got the chance. And in the last shot, you can even see him pulling a sausage straight off the scoop himself. So what about the next task? The one I actually built the robot for, filling the dog's bowl. I filled a large storage container with dry dog food, small pieces the dogs like, and that the scope can actually handle. The goal is simple: grab a proper portion, don't spill half of it on the floor, drive to the bowl, hit the target, and hopefully not mess everything up. As accepted, the first attempts were messy. But I wasn't too worried. My four-legged cleanup crew handled the situation perfectly. With a bit of focus and practice, it started to work surprisingly well. The key was moving the axis very gently, and before driving over the ball, I gave the shovel a short shake, just to get rid of anything that wasn't sitting properly. In the end, it almost felt a bit like operation an excavator, and the task finished exactly where it should, with a full dog bowl.
Now that both tasks are working, the obvious question is, why not automate the whole process? The short answer is, with my current setup, I'm starting to hit some limits. I did try to push the bowl filling task closer to full automation. But the result was a failed planetary gearbox. The team simply gave up. Not because the idea was wrong, but because I lost the kind of direct feedback that I still have when I control the robot manually. So for the next step, the plan is to use harmonic drives at critical points, experiment with different stepper drivers and add a camera to the system. Visual feedback could help me judge motion and react to problems earlier. That's also where things starting getting interesting in terms of AI-based evaluation and learning behaviors. And I haven't forgot the side quest. I definitely haven't forgot the software behind all of this. But this video was about getting the robot to work. The deeper dive will come next. That will be the focus of the next video. And if you made it this far, thanks for watching. If you enjoy the project, I'd be happy about a like or a subscription. See you in the next one.